Okay, so all right, folks. So a very warm Roorkee style Namaskar ji, and the good morning, good afternoon, and good evening, depending on whatever time zone you're logging in from today. And welcome to the 10th installment of the biennial International Conference Strings Conference Series organized by the Indian Strings community, called the Indian Strings Meeting nationally, ISM 2021, hosted this time by IIT Roorkee. So without further ado, I would request our director, Professor Chaturvedi, to kindly inaugurate the conference and say a few words. Professor Chaturvedi, please.
Thank you, Alok. I'm delighted to be in the company, albeit online, of some very distinguished physicists, more precisely string theorists. It is my pleasure to formally inaugurate the 10th edition of Indian Strings Meeting, a biennial international conference. I understand ISM was born in 2002 at Allahabad, and congratulations to the string theorists of India for not only having sustained ISM over a long period, but also having built upon the foundation laid in 2002 to have useful and impactful meetings every 2 years. On behalf of IIT Roorkee, I'm delighted to welcome the speakers and participants of ISM 2021. For the first time, I understand ISM is being organized entirely by an IIT, and I'm happy that it happens to be IIT Roorkee. The fact that it is happening in the 175th year of IIT Roorkee makes it all the more special. As some of you may know, as we approach our 175th year, we are scaling new heights in terms of attracting the brightest students and faculty. For the first time, a student in the top 100 of JEE Advanced has joined IIT Roorkee. The student is ranked 32. Let me briefly also talk about our physics department. It's a fairly large and busy department. Apart from the PhD program, the department offers a 2-year MSc program through JAM, a 5-year BSMS program through JEE Advanced, a 4-year BTech in Engineering Physics program through JEE Advanced, and 2 MTech programs through GATE. I wish it was possible to organize ISM 2021 in a physical mode. That would have given the delegates an opportunity to experience our wonderful campus. I hope meaningful academic interactions will be possible despite the online mode. I wish all the speakers and participants gain by being a part of ISM 2021. Thank you for giving me this opportunity. Thank you.
Thank you, Professor Chaturvedi. Thank you so much. Okay. Maybe all right. So
Alok, there's music coming.
Alok, you are muted. Alok, you are muted.
Sorry.
Alok, there's
sorry,
music coming from someone. You have to mute that person.
Yes.
I hope you have a team to mute random people.
Oh, yeah. So talking about the team, that's a great point. So with the kind permission of our chair of the first session, Professor Spento Wadia, the founding director of the International Center for Theoretical Sciences, Bengaluru. And I guess one of the folks who basically, I would say, acted as a seed for the string theory group at TIFR back in the day. So I want to actually have the backbone of ISM 21, which is the tech support team, consisting of a trio of integrated MSc third-year students. Just with your permission, turn on their cameras and just wave to us, because in my humble opinion, it's always good to assign faces to names. And the names are beautiful. I mean, it's the names say it all. We've got Mohak, we've got Shubham, we've got Lucky. What do you want? So guys, can you turn on your cameras and just wave to us? I have no idea whether they're visible. Maybe one has to scroll.
Yeah, they are visible actually.
Okay. So thank you. Really, guys. Thank you so much. Thank you. And so I think, and one last thing with Spenta's permission, this is exclusively targeting with these very selfish motive of motivating those bright undergraduates who are, I think, logged in today, are going to be logged in for the remainder of the conference, especially from tech institutes. So the speaker number one, day one, session one, is 1987 All India Rank 1, Rajesh Gopakumar, the current director of ICTS. I pray that serves as a huge motivation for quite a few of our students to actually pursue theoretical physics as the first option. So I should shut up now. I apologize. So I request very humbly Spenta to please take over. Spenta.
Okay. So thank you, Alok, for your kind words, and welcome everybody. Good morning, good afternoon, good evening, wherever you are all on this little rock in our solar system. And the first talk is going to be by Rajesh Gopakumar, and I'm looking forward to a very electrifying discussion about this important seminal work on the string gauge duality. The title is From Fields to Strings and Back. Rajesh, take it away.
Thank you, Spenta. Thank you especially to Alok and his team for putting this together and getting us all at least virtually together at this difficult time. It was actually very nice to be reminded that this is the 10th anniversary of the ISM because 2002 we had it at HRI, and it was a really wonderful beginning to this whole thing. Of course, there were precursors at Puri and so on, and Gyan had organized a number of events to bring people together, but I think the string community as a whole probably came together at HRI, and it was it's very nice to reflect back on that time. Many of you were there, and I hope next time we will be able to meet in person, but nevertheless I think Alok has made it as nice as possible by bringing us together. So okay, so let me share my screen. Okay, it's visible, I hope.
Yes, it's visible. That's fine,
yeah.
Please.
So, so thank you for inviting me to give this talk as well. And I will give a sort of an overview, a little bit more pictorial rather than in terms of there'll be some details, but I wanted to try to give you a certain picture of an approach to try to understand gauge string duality in sort of a first principles way. And a lot of the work, at least the more recent work I will be talking about, is in collaboration with Matthias Gaberdiel, and very recent work in the last year or so with a number of people. And I want to highlight Pranabesh, my student who is here, Matthias's student Bob Knighton and Andrea Day, and two VSRP students from the ICER system, Bhopal and Mohali, Faizan and Bharat Kumar. So yeah, so this is a sort of a broad outline of the talk. First, I will try to sort of motivate what I'm trying to do about this approach to derive ADS-CFT, and why free fields are the best place to start in some sense. And some of you have heard me give this motivation, but for the younger people, I think it might be useful. And then I will outline sort of a passage from fields to strings in a very general context. And this is something, it's sort of almost 20 years ago that this sort of outline kind of started taking shape. But more recently, in the case of the ADS-3 CFT duality, in a sense, this passage from fields to strings has been very explicitly realized. And so you can actually see the nuts and bolts of this thing happening in a very concrete example. And then I will try to go the other way around and see how this ties up. And in the ADS3 example will be our jumping off point to go from strings to fields in this. And this will involve proposals for the tensionless limit of the worldsheet theory in the ADS3 CFT2 case, which will, and a generalization of that, a proposal for the free Yang-Mills theory, the super Yang-Mills theory. And in some sense, I'll try to close the circle from fields to strings and back. So, okay, so that's the plan. So the overarching question is, how exactly do large N quantum field theories reorganize themselves into theories of strings, something that had been intuited by 't Hooft nearly maybe half a century ago almost, and which of course received a lot of impetus from the discovery by Maldacena now about a quarter of a century ago on how D-brane physics tells you a sort of a gives you a way in which you can see this happen, or gives you a number of examples where this happens, and the underlying mechanism seems to be a kind of an open-closed string duality. And this picture that I like to flash is kind of a cartoon of that, about how when you sum over the holes of an open string theory describing D-branes, there's a back reaction which alters the background, at least at large 't Hooft coupling, and in some sense you think of it as a closed string background in the dual spacetime. And this is, of course, how Maldacena originally arrived at it, by looking at the near horizon geometry of D3 branes and so on. But to actively implement this idea is very difficult at large 't Hooft coupling, because firstly, there are an infinite number of holes. You have to sum the perturbation. This expansion is a sort of you will have to sort of resum the whole expression, which will lead actually to a change in the background, the back reaction that I mentioned. And this is so it's been a very interesting idea, but but it's very difficult to actually see how it works. And this is why all of our understanding of gauge string duality is through numerous examples from various D-brane configurations. So typically D-brane configurations where we have a sort of a bulk or a gravitational description of the D-branes as well as some geometries. And so if I think of the phase space, so to say, or the very minimal phase space of parameters involved, there's one which is the vertical direction, which is the quantum nature, the quantumness of the theory. And that's measured in the gauge theory by the 1/n effects or string coupling in the worldsheet description. And then there's the horizontal axis, which measures the stringiness of the description, and there's one side which corresponds to the large ADS radius, which is described very well by classical gravity and its higher derivative corrections. This parameter translates into the 't Hooft coupling of the field theory. This was the large 't Hooft coupling or the strong coupling limit of the field theory. But there's this other corner, which is the perturbative quantum field theory limit, in which the 't Hooft parameter is very small, but of course the ADS is then very highly curved or tensionless. It's the extreme stringy regime. And this is the sort of typical dictionary you have. So, but the advantage of looking at this side is that we know what perturbative quantum field theory is. And in particular, in this open closed string duality, there's only a finite number of holes to sum over, definitely at zero coupling. And then you can sort of stratify it by the usual Feynman diagram expansion as you go away from there. There's, of course, a well-defined genus expansion still at zero coupling. And you can, if you go away from zero coupling, you have the whole machinery of perturbative quantum field theory behind you to understand them. And and indeed, what that machinery is basically computing free field correlators or Wick contractions. And we'll focus on two test cases to sort of, when we'll shift focus to this end, as I said, this is the motivation part I mentioned, we'll shift focus to this end, and we'll focus in the rest of the talk on two particular examples where we'll look at the tensionless limit of this dual string theory, or from the gauge theory point of view, focus on free theories, namely the so-called free symmetric orbifold over here, or the free n=4 super Yang-Mills theory over here.
Rajesh, can I ask a question about that diagram?
Sure.
About that picture?
Yes.
You know, somehow you seem to be implying that we can, the lampposts are really bottom left and bottom right. But
Yes.
Isn't it possible to go up by considering a solvable field theory, for example?
Yes. Yeah. So free field theory, of course, you can go up here.
Not just free, I would say. I mean, you could take a 2D.
I mean, you can in the perturbative regime. Yeah. So this, and perhaps there would be integrable models in which, and in some sense, in n=4 Yang-Mills and many other theories, you can go quite a bit here. You have many exact results in the 't Hooft coupling, so you can go both horizontally and to some extent vertically. Yeah. So, but this is the canonical case. I just wanted to focus on those two because those are the places I will be mostly working on. I will be working at very large n, so I will be mostly looking at things in the genus 0 on the worldsheet, and yeah, so that's the regime, but we can talk about other extensions as well.
Thanks.
So I want to say a couple of words about what would constitute, at least in my eyes, a derivation, at least the beginning of a derivation. And I'll take as an operational definition the equality of Euclidean correlators on both sides of the duality. Now, there are many, you can consider Lorentzian correlators, you can consider non-local operators, there's many other things, entanglement, entropy, various measures that are there, but I will focus on this limited class because I think that already gives you a lot tells you a lot about the innards of this duality, and then one can hope to address others. So for this class of observables, the idea is that you're relating single trace operators on the left-hand side. So these O's are things in a gauge theory which would have a single trace of a gauge invariant. So it's a gauge invariant quantity, but with a single trace. And they are labeled by positions x1 to xn. So the x's for me will always denote the position of the field theory variable, and we are looking at a Euclidean free theory, which is conformal. So we can think of it on the sphere, the d-dimensional sphere. And these are other labels, which H's will be essentially the conformal dimensions, and W's are other labels which you needn't bother about right now. Now, the fact that the field theory has a well-defined 1/n expansion means that you can pick out the genus G contribution of this correlator, and the idea is that it should map to the genus G contribution of the corresponding string amplitude, which is also given by a worldsheet correlator. Now it's on the two-dimensional worldsheet of the string. So this correlator, the Z's, will define the worldsheet coordinates, and we'll compare genus by genus. So here it will be a correlator on a Riemann surface or a worldsheet of genus G with n punctures. N is the number here. And then, of course, we are instructed to integrate over the moduli space of all these worldsheets. And that's what this right-hand side represents. And these are the physical vertex operators of the closed string dual. So it's a statement of this equality for all n, all g, all x's, all w's, etc. So it's a very vast kind of equality that you want to match. So this is.
I have a question.
Actually, I think if we can have the questions at the end, I think that would be better. I think
Yes.
that was. This, of course, when I write such an equality, it presupposes a dictionary between the single trace operators and the vertex operators. So that is essentially a statement about the matching of the spectrum, that the single trace operators correspond to physical single particle states of the string theory, and there's a match of the conformal dimension with the sort of the space-time energy of the dual string theory. Now, the nice thing which I like about this operational definition is that both sides on over here have can be in principle autonomously defined. The left-hand side is a quantum field theory correlator at a fixed point. I mean, it's a free theory, so it's sort of trivial in some ways. And the right-hand side also, we believe, at least it's not guaranteed, but the working hypothesis is that there is a sigma model, a two-dimensional CFT on the right-hand side, and these are physical correlators. That sigma model can be quantized in the usual method, and this right-hand side it gives you a physical correlator of that dual string theory, and there's an integral over this moduli space. And so, in principle, it's a mathematically well-posed question, and one of the main goals is to try to make this equality manifest. That I mean, of course, you can check case by case, and that'll be you get confidence in a duality. But to ultimately understand it, you want to, in a way, tautologize the correspondence, or say that this side is manifestly the same as that side, because it's, I think, our job as physicists to sort of demystify this remarkable equality. But I want to point out an apparent asymmetry in this equality when we kind of try to match these sides. At first sight, it seems almost as if if we are trying to, if it's easier in some ways to go from strings to fields, because if you can try to compute this correlator of the 2D CFT and then integrate it, and you can try to do this. But going from the other way, from the left-hand side to the right-hand side, in some ways, you think you need to reconstruct this worldsheet integrand, and that is, of course, not unique. You can have total derivative terms, or in the language of the usual string theory, BRST exact terms, etc. Nevertheless, I think that, as I will try to argue, there is a canonical or a natural way in which you can go from the left-hand side to the right-hand side. And that was the ideas I was developing almost 20 years ago. And the basic idea, and I'll flesh it out a little more in the next few slides, is that, and this is now I'll going to the second part, the sort of the general passage that I'm going to, this thing is actually in the left-hand side also, there is a hidden sum. This side, you think of the integral on moduli space as a sum over the world sheets of the string. But the left-hand side also, when we actually evaluated, you sum over different Feynman diagrams, which are in a sense distinct world line topologies of the corresponding gauge theory or the field theory. And so there is a sum on this side, there's a sum on that side. Now that seems to muddy things even more. I mean, now how do you kind of try to make a correspondence? So the claim is that each Feynman graph corresponds to a closed string worldsheet. So that sum is, in some sense, you are trying to equate the summands or the integrands on both sides. So the strong claim is that each Feynman diagram corresponds to a closed string worldsheet, and there's a very canonical way to do this. And this was the proposal which exploited a certain parametrization of the moduli space, which is very tailor-made for this open-closed string duality, and in a way, I think really implements it mathematically. And this I will explain a bit this Strabel parametrization of the moduli space, but I just want to point out at this stage that this is in some sense refining the Toft's original idea, where Toft assigned a genus to each Feynman graph. So it made a correspondence between a class of Feynman diagrams and a set class of worldsheets. Now you're going further and sort of assigning each Feynman diagram to to a particular world sheet. And there's a and this basically the geometry underlying this treble parametrization is that of gluing strips. So you can, Toft famously taught us that you can think of the Feynman diagrams of the large N theory as sort of these double line strips, which we now think of in the D-Brain language as open string world sheets. So these strips can be glued in a very canonical way to form the closed string world sheets, and this is what we will try to exploit. So,
Girish, can I interrupt? There is
yes,
an
please.
Overwhelming request to take short questions from a lot of people. So
okay.
I think we can just do that. But
Sure.
I'll in case it goes too long.
Yeah, so I'll leave it to your judgment.
Sure. Okay. So anybody has a short question at this juncture can ask, please.
Yeah, so I have a question. By free, do you mean that there are no interaction vertices?
So the free theory will be defined as the limit as the G Yang-Mills coupling goes to 0 of the n equal to 4 Yang-Mills. It will be given by, so when we are considering these correlators, there will be no internal vertices. Of course, there will be external vertices, and there will be big contractions between single trace operators.
But how can there be external vertices if there are no internal vertices?
I mean, there are gauge invariant operators in the Yang-Mills theory, which are products of whatever the fields are. So traces of single trace operators, and the whole definition, the physical observables in the free Yang-Mills theory are these correlators. So you can represent them diagrammatically. It is something like what I have here, that you have these, in fact, these Zs over here are vertices. So you can think of, I mean, here I've drawn many Feynman diagrams, but if you count the number of contractions, that's an operator trace with phi to that many this thing. So that's the left-hand side of the equality that I was mentioning. So you can consider product as this is, in this case, there's a 4-point function. There's point at infinity as well, which is where all these lines go and contract. And so it's a 4-point function of traces of single trace operators with a finite number of fields in them. And so you're considering all these big contractions. Yeah. So if there are no further questions, let me explain this a little more. So this canonical picture that I was mentioning is the following, and so this is a representation of the Feynman diagram. Now you can think of this Feynman diagram. So there are all these strips over here. So you can associate a big strip whose width is proportional to the number of the strips of each color. So they are color coded because of the big contraction. So Z1, these ones are contracting with Z4, these are contracting with Z3, and this with the Z2, and so on. So that's why they're color coded. But you can think of each of these individual strips as, firstly, you glue together things which are homotopic to each other into one fat strip of width. You assign a width which is proportional to the number of big contractions. And you can think of these strips as conformal to these quadrilateral regions. And you can associate a closed string surface where the original points are poles, and these strips are all glued together along this thick line over here. So this is what in the previous this thing, oops, how do I go back? So here you could see that there's a kind of a place where all the three things meet, and you get a kind of a graph here. And so this is the That's what, in general, this colored lines here represent. You have these strips which are all glued at these along these graphs and along the edges of these graphs. And the width of each of these lines of the graph is, as I said, proportional to the number of these Wick contractions. This associates a very canonical, this is a mathematical construction of the moduli space of the closed string world sheets. And just specifying these widths, it gives you a unique point on the moduli space. And so this is a very natural mathematical construction, and it associates to this set of Wick contractions, a given so-called Strebel surface, and these points become the poles of a corresponding quadratic differential, the Strebel differential, the original insertion Zs, and the vertices of the graph where these where these strips are glued, these vertices become the zeros of the Strebel differential. So what is this Strebel differential? The Strebel differential is a quadratic differential which, as I said, foliates the Riemann surface into what are called horizontal trajectories. There's a technical definition, but never mind. There's a very nice foliation, which is like these closed circles like isobars or whatever, except at this graph, which is where it becomes a kind of a graph and it has these vertices, which is called the critical horizontal trajectory or the critical graph. So each of these are sort of disks with a single pole of the Strebel differential. And in fact, it's with a one pole, which is a double pole of the Strebel differential. And these zeros are the zeros are where this graph has these vertices, as I said. And you can consider the so-called Strebel length, which is the integral between two zeros of the Strebel differential. And this is what, as I said, it's the width that I was mentioning of the strip earlier. And these lengths are what parameterize the moduli space. And we'll often consider the case where these lengths are integers, and because in the canonical way to associate to a free field Wick contraction, like in my previous figure, was to the number of Wick contractions. And so we'll often consider that case, and I can discuss more later. So that's the sort of the general picture. Now, I must stress, this was a proposal. This was a proposal when I was making it many years ago, and you can believe it. It of course had a certain level of plausibility and but it's a proposal for how to associate world sheets to world lines. The very nice thing that happened recently was in the context of the ADS3 CFT2 correspondence, you could actually see this explicitly realized, and without having to sort of make any proposal or guesses or anything like that. It just came out of the box, so to say. So firstly, what is so for ADS3 CFT2 a couple of years ago with Lawrence Eberhardt and Matthias Gaberdiel, we made a proposal for the dual for the tensionless limit of the ADS3 CFT correspondence. We identified the tensionless limit as the point of this, let's say, with the T4 compactification, this background, with 1 unit of NS flux through the ADS3 and the S3. And we claim that this is the same as the symmetric product of the T4 theory, in this case in the large N limit with these couplings. So the symmetric product is CFT is a very well-studied two-dimensional CFT. It has arisen in the context of the black hole microstate counting and so on and so forth. This left-hand side is you compute correlators of so-called single cycle states, analog of single trace operators, and now it's on a two-dimensional sphere because we are in 2 dimensions. The boundary theory is on the S2. And this side is string theory, which is also well defined because it's a theory with NS flux, and you know a worldsheet description of this side as well. But let me, since we are still on the fields to strings, let me concentrate on the left-hand side. And the left-hand side, the correlators are computed. It's been known actually since Lunin and Mathur, again about 20 years ago, that there's a very nice way to compute correlators in the symmetric orbifold CFT, which is similar to how people compute things in CFTs with using the replica trick. So what you do is you can, instead of computing the correlators directly off this T4 CFT, you lift the correlator to an auxiliary space, an auxiliary two-dimensional surface on which the fields are single valued, and you have a T4 CFT, not this symmetric product. You just have a T4 CFT, but you have a more complicated worldsheet, which is a covering space of the original space-time, the S2. And in fact, it was even guessed at that time that this covering space seems to play the role of a worldsheet. And now actually we see this very clearly realized. But in any case, I will come to the string theory a little later. So the idea of the Lunin-Mathur computation is that you can compute this side by summing over contributions from various covering maps from this auxiliary space, or aka worldsheet, to the S2 over here. And for fixed number, if I fix these xi's, as I would normally do, there's a discrete number of these covering maps. If I fix all these branching data, which is the xi and the degree of this branching, which is, by the way, related to the twist of the cycle in the orbifold theory, the length of the twist of the cycle, and in this side will be related to what is called spectral flow parameter. But in any case, this is the part of the branching data that you specify when you compute these correlators in terms of these covering maps. And there are actually a discrete number of covering maps, and there's a nice way to associate them with Feynman diagrams. Each of the contributions to the correlator here can be associated to a Feynman diagram, much like a free field Feynman diagram. And this was pointed out by Bachman, Rastelli, and Razamat more than 10 years ago. And just to give you a brief idea of what it is. So if we are computing a 4-point function of, and this X is my space-time, the two-dimensional sphere where the CFT lives. If I'm computing a 4-point function, I draw a curve through that 4-point function, and which encloses, let's say, X equal to infinity. And I draw a solid curve, and I kind of have a dashed curve through it, a bifundamental line that I draw. Now I pull it back by this covering map. There is a covering map from this auxiliary worldsheet space, the Z space. And it's a multi-cover, so there will be multiple images of the pre-images of this. This shaded region will go into, in this case, 3 shaded regions. Each of these will be poles, the pre-images of the poles, or the poles of the covering map, gamma of Z. And so there's a Feynman diagram. This side begins to look like a Feynman diagram. And in fact, when you have a very large covering map, you can begin to see it starts becoming really like a usual big contraction Feynman diagram. And this is sort of the neighborhood of between 2 vertices I and J. You have multiple of these pre-images, etc. So you can have multiple big contractions between vertices, and there will be a sequence of these poles, these pre-images of these poles of this covering map. And the thing that was very nice is that in a limit, when you take this twist or the W's, the cover, the branching data, the number of big contractions to be very large, these poles start coalescing into cuts, and you start getting these cuts on the dual on this covering space. And in fact, this becomes precisely the Strebel graph. You can actually show that. And it's very nice because there's a very canonical thing you can associate, a canonical quadratic differential you can associate to the covering map, which is the Schwartzian of the covering map. And the Schwartzian of the covering map in this large twist limit actually becomes this quadratic differential that I mentioned, the Strebel differential. It has exactly the properties that the Strebel differential I mentioned has, namely it has these double poles and this real lengths and everything. So it is the Strebel differential, which is normally very hard to find explicitly, but in this large twist limit, it takes a very simple form, being the Schwartzian of this covering map. So this is what I was saying, that now for at least for large twists, you can see that each Feynman diagram, and namely each of those pictures that I had in the previous slide, corresponds actually to a point on the moduli space where the Strebel lengths are proportional to the, in fact, the Strebel lengths you can now see from the definition of the Schwartzian. Again, you don't have to propose anything. You see directly from the Schwartzian, the definition, from the fact that the Schwartzian is the Strebel differential, you see that the Strebel lengths, this integral bit along these, the integral along these between these zeros, these are proportional to the number of the Wick contractions. In a way, it just comes out. This comes out through a very nice auxiliary matrix model whose spectral curve gives the Strebel differential, and which is the thing that is the Schwartzian, etc. But I don't want to go into that in detail right now. But the point now is that, in fact, more than what could be said 20 years ago, you actually now learn what the integrand on the moduli space is also. So when I mentioned earlier about associating fields and strings, I talked about associating each Feynman diagram to a string worldsheet, but now the summand itself, each integrand or piece in this sum, you can see what it is because Luhn and Mathur gave you a prescription of what it should be. It is given by a certain Liouville action. And when you compute what that Liouville action is now using this realization, you find that it is this nothing but the Strebel area, the area of the graph under the area measured in the sort of natural Strebel metric that you associate to the Strebel differential. So this is how so you see now the passage from fields to strings very explicitly in this example. And to really close this, you need to show that the string worldsheet also gives you exactly this, and this we were able to show from the explicit form of the k equal to 1 string theory, showed actually that you do get a localization on the moduli space. There are very specific points that it gets contributions from, which correspond to the covering maps. There's normally in the string correlator, you get a contribution everywhere on the moduli space. But Luhn and Mathur told you there are only a discrete number of contributions from these covering maps. And the string worldsheet is clever enough to see that there is this discrete set of covering maps. And the integrand is given by, in this case, the semi-classical worldsheet action, which agrees with this Strebel area. So you can really close this. And this very unusual localization property on the moduli space, we could understand later that it follows from something like a twistor incidence relation, which will actually play a role in the second half of my talk. Well, yeah, the second half of my talk, which I'm coming to now. So now let me go from the strings to the fields. So that let's see how things start tying up from the string theory side. So for ADS3, as I said, there's a very explicit worldsheet description. You have a free field description actually at this k equals to 1 point because there's a Wess-Zumino-Witten model based on the supergroup, and it's a kind of a gauge linear sigma model. And despite it being a highly curved ADS3, the worldsheet description is in terms of free fields. It's a bit like the SU2 level 1 theory. This is just a souped up version of the SU2 level 1. Instead of just having some fermions, you now have some funny bosons as well, bosons with the wrong statistics. That's what symplectic bosons are. So but there's a geometric picture of what this free field description is. There are actually some kind of twister variables, and this will be important as we go to the ADS5 case. I mentioned this before, that the twisted sectors of the orbifold CFT, which are labeled by the lengths of the twist, correspond to what are called the spectrally flowed sectors, which I don't have time now to explain, but maybe those of you familiar with this will understand. And indeed, as I said, the worldsheet correlators are delta function localized, and the semi-classical worldsheet is actually at the boundary of ADS3. You can write down the semi-classical string configurations which contribute to the worldsheet path integral, and they give exactly the Lunin-Mathur correlators, as I said, closing the circle in this particular case, I think very satisfyingly. This is sort of the logic of the flowchart. If you're kind of confused, this side is the sort of the field theory side. As I said, there's the correspondence is that there's a Feynman graph, and the dual to the Feynman graph is the so-called Strebel graph, which is associated with the Strebel differential. In this particular case of ADS3, this Feynman graph was related to these covering map contributions, and through this auxiliary matrix model, you got the spectral curve, which has the cuts, and then this spectral curve was in the large twist limit was described by the Schwartzian, which, as I said, turns out to be the Strebel differential. And this identification is sort of what is important for connecting with the worldsheet analysis, which, as I mentioned, the worldsheet gets contributions localized at this point, and these correspond to these very special points on the moduli space where the Strebel lengths are integers. Okay, so in the remaining 15 minutes, I guess, of my talk, I'll try to say a bit about how this generalizes to the ADS5 case, or what we are proposing for the ADS5 case for free n equals to 4 superyoung. So this ADS3, as I mentioned, there's a sort of a sigma model description in terms of these free bosons and free fermions, which can be assembled into some kind of ambi-twister variables in the twister language. This viewpoint is perhaps not so significant for ADS3 times S3, where you could think of it in more conventional ways, but I think it is very crucial when you generalize to the ADS5 times S5, where you have the corresponding ambi-twister variables, which are well-known twister description of the boundary theory, and has cropped up in the description of free or tree level n equals to 4 super Yang-Mills amplitudes in an ambi-twister open string theory. In a sense, what we are proposing is a kind of a closed string cousin of this description based on these fields, which are the natural generalization of the field. So instead of this sigma model, we consider a sigma model now, which in a way realizes the PSU 2,2/4 supergroup relevant for ADS5 times S5. Supporting evidence for this proposal is also the fact that it ties in very naturally in giving a kind of a covariant description to the BMN light cone gauge string theory that people had studied starting 20 years ago, and which led to all the integrability developments, etc. So let me just quickly give a picture of what this worldsheet description is. As I said, there are these twisters fields, and they give a free field representation of the supergroup at level 1. You just construct currents by bilinears of these fields, and you have to impose a certain constraint, which is a very important gauge constraint. So in a way, it's a gauge linear sigma model. You have these free theories with a U1 gauge field, which imposes this Gauss law constraint on the worldsheet. There's this crucial ingredient of spectral flow, which I can't do really justice to, but it's many of you may have seen this in the context of ADS3. It's an automorphism of the supergroup. Basically, you generate new representations labeled by a positive integer W, which you can think of as built from so-called a spectrally flowed vacuum state by the action of these spectrally flowed fields. So you can think of this as a kind of a rotated version of your original highest weight representations of this Weissenberg-Witten representations, but these are non-highest weight once you do this rotation, because now there are some seemingly positive modes which will be, some positive modes which will not annihilate the vacuum, etc. But nevertheless, in ADS3 saw that they give you very well-defined physical string states. So in any case, you consider this Fock space for each W, and we consider this generated by a finite number of these so-called wedge modes. There's a very canonical set of modes whose mode number lies in this finite region between W-1/2 and plus W-1/2. So we consider a Fock space built out of the modes which do not annihilate this vacuum, which are about half the modes in the wedge. And then, of course, there are negative out of the wedge modes, which have mode numbers less than this in this interval. So just to kind of give you some anchor, W equals to 0 is, of course, the spectrally non-flowed sector. That's the usual NS sector. There's the W equals to 1, which is now integer moded. And in fact, the wedge you see is just 0, and it has only 0 modes in the wedge. And that's the Ramond sector. And together, in fact, the W equals to 1 sector actually generates the so-called singleton representation of this supergroup. By the way, for those who are familiar with the BMN string, this W will play the role of the P plus of the light cone gauge of the BMN string. That's, I think, a very useful intuition to have. So we make a claim which ultimately should be borne out by a quantization of the worldsheet theory, that you can go to a physical gauge of this worldsheet theory. So by the way, the original theory has ghosts as well. It has vanishing central charge, then you impose, then you add the ghost system, and we would like to claim that there's an underlying worldsheet n equals to 4 structure, which has the corresponding n equals to 4 ghosts, which also have central charge 0, and so that you can get critical string theory. And the claim is that in a physical gauge, all the underlying constraints from the n equals to 4 symmetry, or the large worldsheet symmetry you have, allows you to gauge away most of the modes, namely all those out of the wedge modes, and leaving only these modes in this wedge, which correspond to effectively the W bits. And then you consider the Fock space generated by them and impose certain residual physical conditions, somewhat like you impose in light cone gauge, that L0 is sort of 0 mod W. And this, of course, there's the important gauge constraint, that the residual gauge constraint that you still need to impose. And this condition A is, if you wish, some kind of a discrete translational invariance on the worldsheet with these W bits. It's a sort of a cyclicity, and this gauge constraint is the very natural one, which is that each of these bits together form a singleton. And this is particularly more natural if you look at the site variables, which is a discrete Fourier transform of these original twistor variables. So phis are any twistor variables. So this reproduces once you impose this condition, this on the nose reproduces the large N gauge invariant spectrum of single trace operators built with so-called W letters of the n equal to 4 super-Yang-null. More specifically, what you get are, you take when the W spectrally flowed sector, you take the singleton representation, tensor it W times, and impose a cyclicity condition, which is what that L0 is equal to 0 mod W imposes. And then you sum over all W from 0 to infinity. W equals to 0 is very trivial. It is just the, as I said, the Neveu-Schwarz vacuum. And that's once you impose the physical state conditions, that's the only state that survives. And that's naturally identified with the identity operator in the Super-Yang-Mills theory. This W equals to 1 corresponds to single letters. As I said, these are the singleton representations where you just have single fields in a SUN Yang-Mills theory. If you take the trace of these fields, you don't get anything, but in a UN Yang-Mills theory, you have this. So in a sense, what you get is sort of more naturally the dual of the UN Yang-Mills theory. Of course, the singleton can be decoupled. And for W equals to 2, just to illustrate what you get from you find that there are physical states with L0 equals to 0, not just mod W, identically 0. These correspond to the BPS stress tensor multiplet, which has delta equals to 2, that is this multiplet with this lowest state and descendants. And in fact, it's a general statement that the L0 equals to 0 state corresponds to all the BPS multiplet. The L0 not equals to 0 mod W, in this case 0 mod 2, the first state is this -2, and that corresponds to the non-BPS Konishi multiplet, this and its descendants. And for in general, -2p corresponds to all the higher spin multiplets. So these are the things with 2 letters, which form the usual higher spin currents from bilinears of the fields. And you can do this for any W, and you see a very nice organization of the spectrum of the free Super-Yang-Mills, which is in a way a covariant organization, because you're not just organizing now by W, but you can actually further stratify by the eigenvalues of L0. And you see a very nice parallel to the BMN spectrum, because it is now, the BMN spectrum is, of course, in terms of the light cone momentum, but it's very similar to what you have over here, at least at large W, they seem to be the same. Finally, in the last 5 minutes, let me just tell you about something which pushes things beyond the spectrum, and based on recent work with Pranabesh, Faizan, and Bharat. So you can try to build a geometric picture for describing correlators in this case. As I said, after you match the spectrum, the idea is to see if you can tautologize the equality of correlators between the left-hand side, the field theory side, and the string theory side. And in ADS3, as I mentioned, there's a very beautiful picture which allows you to sort of the Slunen-Mathur picture, which is realizes this equivalence between the realizes this way of going from fields to strings through the Strebel parametrization of moduli space. Can we see an indication of this in the ADS5 case? And this is what we have begun to do here. And you can actually consider now the generalization. There's no natural generalization of the Lunen-Mathur picture directly, but because that was in a way special to the ADS3. But there's the natural way to generalize is through considering covering maps of the twistor space. And once again, look at world sheets which are close to the boundary of ADS5. And what we propose is that these being twistor variables, and these are actually the twistor variables for ADS5. There's the twistor description of ADS5 has a very natural set of, is realized with a natural set of so-called incidence relations, which anyone who has studied twistors will know is one of the most fundamental relations. It is the twistor correspondence between space-time and the twistor variables. So this twistor incidence relations for ADS5, we propose that these hold at the stringy level now as fields. So that's why these are functions of Z, and these are holomorphic functions of Z. And the twistor variables, these X's are the boundary space-time of the ADS5, and R is the radial direction. And there's a similar similar set of incidence relations for the others. And now there's a very natural set of reality conditions you have to also impose on the twistor variables. And these are Euclidean reality conditions which relate lambda with the complex conjugate of lambda, and in a way with the anti-holomorphic fields. And in terms of them, the twistor correspondence in Euclidean signature allows you to solve for the space-time variables in terms of the twistor variables. And you see now it's not holomorphic, and that's in ADS5, there isn't a very direct holomorphy in terms of the space-time variables. It's the twistor variables which are really holomorphic. And at least in a special set of kinematic configurations, when the points lie on a plane or on a sphere inside the boundary, you actually can explicitly write down these holomorphic covering maps, like in the ADS3, for instance, for a 2-point function of trace phi to the W, phi bar to the W, BPS states. You can write down it's a kind of a simple branch cover. The V's are essentially the space-time positions, between xi and xj. If you have, this corresponds to a covering map for a 2-point function to xi and xj. And you have this explicit covering map and the twistors. And the quite very nice thing that you see is that very parallel to the ADS3 case, you can actually map these variables, these Z variables, to the strip, conformally map them to the strip. And the Schwartzian is actually a constant, which is what you actually have for this treble differential on a strip. And very nicely, this treble differential once again reproduces the propagators of Yang-Mills fields through the so-called treble area, which, remember, in the ADS3 case, I mentioned that the integrand on the moduli space gives you the Lunin-Mathur integrands. And here you want the Feynman diagrams should give you the Feynman diagrams corresponding to any correlator should give you the Feynman propagators as the weight, and then you sum over all the Feynman diagrams, and you get a very similar picture. I don't have, let me just show you this diagram, that you can have the strip, as I said, and the strip is of width W, and of course, in a multi-point correlator, you can conformally map all these strips. This is like in the picture I showed you, to these quadrilaterals. There are many of them meeting at a point, and you can compute the treble area of the whole world sheet by adding up the contributions for each of these quadrilaterals, adding up these treble areas, and the additive treble areas lead to multiplicative Feynman propagators, like you are used to doing in a field theory. You have the product of propagators from here to here, and in fact, it comes out very neatly, because you see that the treble area, in fact, with you need to regulate the treble area because it's that of a strip, and so it's sort of infinite. But if you regulate it with the very natural imposing a space-time cutoff, you see that the treble area gives you the Feynman propagator up to a multiplicative renormalization, which you would normally have to do for each of the operators due to the short distance singularities in the field.
Rajesh,
yes.
How long will you take?
I'm essentially done.
Right. Okay.
So this is my last slide. So so that's this thing that so let me just summarize by saying that we've exhibited these test cases, the tensionless ADS3 CFT2 to a large extent, and begun on the ADS5 CFT4 case, where this general program of reassembling large N quantum field theories into string theories can be very explicitly carried out. And because there is a dual tractable worldsheet theory, we can try to close the circle from the strings to the fields as well. And this then holds out the hope that once you understand these cases very well, you can generalize to general large N quantum field theories, because you need not necessarily have beforehand the worldsheet description. The field theory would give you, through this treble construction, description of the dual worldsheet, at least the dual worldsheet correlators. Now, before we do that, there are many other things in these examples itself that needs to be understood better, I feel. One of the most important things is a first principles quantization of the worldsheet theory and getting the physical states from these twistor worldsheet theories. They're very unusual and they have many complicating features, which is what has made the task difficult, but it's a technical hurdle, which I think will be overcome. There's an underlying topological string nature to all this, and especially if you the localization on moduli space is often is a signature of the topological string description. So many indicators all along the way of an underlying topological string description, which I think will be ultimately the natural way to view the worldsheet theories. And I mentioned about these correlators in the free n equals to 4 Yang-Mills and the geometric picture of twistors, which seems to capture many aspects of these free correlators. I think there's much more to be done there to flesh it out and to understand these twistor geometry of these twistor incidence relations from the worldsheet perspective. And of course, you would like to perturb away from the lambda equals to 0 and see this integrable spin chain description arise from the worldsheet theory. And it's very encouraging that all the ingredients are there. The bit picture is there, which really is what the building block of the integrable spin picture. And in fact, these twistor variables arise very naturally in the integrability approach to understanding the theory away from lambda equals to 0. And this would give the current picture would give some kind of a covariant worldsheet description of that integrability picture. So that's all, and thank you.
So thank you, Rajesh, for an exceptionally clear talk. And we have a little time for some questions, but before I throw it open to the audience, there is one question from Nabamita in the chat. And Nabamita, could you please ask the question yourself?
Yes. Just 1 minute.
You have echo because 2 devices are on with a microphone.
Okay, sorry for that. So
No,
I just wanted to ask that the operational definition for the proof that Rajesh, you provided in the second slide of yours.
Yeah. Sorry.
Yes, the first equation is. So for well-known examples of ADS CFT that we know, suppose say for ADS 4 CFT3s or ADS 5 CFT4, this is this must be known, right? I mean, for examples that we know, there this relation must be true, right?
So what has been checked is, of course, the left-hand side, you can compute when you can compute. Of course, in the free theory, you can compute, but most of the checks that people have done are for the spectrum, of course, but where you have studied correlators, it has been at strong coupling. So in the opposite regime, where the right-hand side is given by some supergravity on shell amplitude, and then you can check. Of course, there are many cases which are BPS protected and so on, like in the famous n equals to 4, the example itself, Shiraz and others had in the early days itself shown the equality of the 3-point function of BPS states. So there are cases which are either protected by BPS, these things, or through localization, you can compute certain things. So in those cases, people have checked individually, but it is, of course, not known in general why it is true, or even if it is true. I mean, it's very difficult. There's an infinite number of checks here. And certainly no one, I think, has looked beyond 4-point functions.
Yeah. So my question was for those very specific limits, at least this relation is well understood for, say, for n equal to 4 Yang-Mills and the corresponding supergravity theory in the limit.
I mean, it's not understood. The right-hand side is not understood in a worldsheet description, but yes, from a space-time description, it is understood. You have the so-called string field theory, which in this case is just a supergravity theory.
Thank you.
Okay. I think there are some raised hands. The first is Ashok Sen. Ashok, could you please ask your question?
Yeah. So my question is the following: that you described it in the Euclidean version, right?
Yes.
But in the Lorentzian version, people have considered this quantum error correction mode to reconstruct the bulk of ADS. And since you have a free field theory correspondence, I'm wondering whether one can explicitly check that, or is it will it become just tautology?
The free field limit is a bit of a singular limit in that the worldsheet is effectively at the boundary. So in a way, the bulk and the boundary distinction itself becomes very fuzzy. It's firstly of string scale. The whole bulk itself is of string scale. And the worldsheets that dominate are effectively at the boundary. So the notion of the reconstructing the bulk in a sharp way, when we don't have locality at that scale, the ADS scale is the string scale. So I'm not very sure how it would work.
Okay. See, my understanding is that this bulk reconstruction that people do, I mean, there you do take all scales to be of the same order. Right? Nevertheless, you reconstruct the bulk because you take the overall size, right? Not the curvature is of the order of the string scale, but you just take the overall size to be very large, and you construct a local bulk at a scale larger than the ADS scale.
Yeah, but here, how would that be possible? I mean, here the bulk, it's, you're talking of the infinite ADS.
Exactly. I think when people talk about bulk locality, that's what they mean. Because I don't think that they have constructed locality. I mean, they have understood locality beyond the ADS scale. Right. So it seems to be a good testing ground for.
Yeah. So there is a kind of a UVIR, this thing, in the sense that the depth to which it sort of goes in is related to the separation in the boundary of the correlators. And so there may be a way in which you can sort of see how, because the string does probe more of the inside depending on the positions of the insertions on the boundary. And there may be a way to do it, but the picture that I have, at least, of how this bulk would be reconstructed is more like an RG picture, that you have these bits on the boundary, and these bits, like just by integrating out the entanglement between adjacent bits, you're kind of going deeper into the boundary, like this tensor network picture. So there may be something like that, because you have a free theory indeed, and you can just look at the entanglement structure of the spin bits of this free theory and probably see this very explicitly. That is indeed, it is possible, but I haven't thought anything more about it concretely.
Okay, the next question, Sunil Mukhi.
Yeah.
Could you ask your question, please?
Yeah, Rajesh, the conventional wisdom about string theory on ADS5 cross S5 would be that the worldsheet theory has a Ramon-Ramon background, which is difficult to quantize and so on. And it's a large background, right? It's proportional to N. Now you have a free field, an alternate free field description of the same string theory in a limit where lambda goes to 0. So is it sort of a claim that in this limit, or more generally, there's a map from a non-trivial sigma mod, that non-trivial Ramon-Ramon sigma model to this free theory? Is that somehow one interpretation of what you have done?
Yeah, I mean, it would be very nice to understand the connection to a conventional sigma model description. So the best I can say is that firstly, we are now in a highly curved ADS regime, and in some sense, the Ramon-Ramon flux is minimal. So at lambda equals to 0, strictly speaking, the Ramon-Ramon flux in a way doesn't really enter, because Ramon-Ramon flux enters as G string n, and G string n going to 0 is really a point where you don't have in some sense a Ramon-Ramon flux, but nevertheless something is stabilizing that background. It is it's there in some quantum sense. It is there, I think, and that's what I think this level 1 theory is doing, a bit like SU2 level 1 theory does. It's a highly curved sphere, and in fact, it becomes a circle in that limit.
Exactly, it's a map from some very curved manifold to a flat
thing. So
simpler variables.
So but here, that's why I feel the underlying geometry is best thought of in the language of the twistor space of ADS5. This is and because that's the interpretation of this free field theory. The free fields are not any old free fields. They have a geometric interpretation as giving the twistor description of ADS5. So, and the twistor correspondence of Penrose allows you to make a correspondence with space-time, but it's a very non-trivial correspondence. So I think anything will have to flesh out this twistor correspondence at the stringy level, any map between these variables and the usual space-time variables.
Okay, there is a question from ICTS. Please go ahead.
Hello.
Hi, Loga.
Hi, Rajesh. So in this, I just wanted to ask, in this twistor way of describing this world sheet, like, do we understand how to think about d-branes in the bulk, or the d-branes ending in the boundary theory?
Absolutely. I think, I mean, it's not something I have looked at in any deep sense. In the ADS3 case, actually, Matthias and his collaborators have a paper on the d-branes in the ADS3 case, which in terms of these free field description, the corresponding free field descriptions in ADS3, which actually have a very nice correspondence with the d-branes of the symmetric orbifold theory as well. So I presume something like this must happen here, because this is again a free field theory. You can look at the corresponding d-brane backgrounds. And indeed, I think these are very interesting things, because I think there will be an effective description on the d-branes, which I think should give you the Berkowitz open string theory, the things that Witten and Berkowitz and then Mason, Skinner and all used to describe free Yang-Mills amplitudes using a kind of an open string theory. I think that should tie up with the d-branes in this background. But that is, of course, it's just speculation of them.
Okay, Alok, please ask your question.
Hi, Rajesh. I just have a small question about the incidence relation that you showed in the end in the.
Yes.
Yeah. So the usual twistor in the Minkowski space, these mu's are constructed simply out of the undotted spinors. Right? I mean, the right hand side is 0. I was just.
Exactly. So this is the twistor incidence relations for ADS5. They're not the same as the incidence relations for Minkowski space. And they reduce to that. In fact, when this is the radial direction. So there is a way in which you can take the limit of the ADS5 incidence relations and recover the incidence relations on the boundary, which are the usual incidence relations. But this is then what you recover on the boundary is the so-called ambitwistor description of the boundary theory, and the ambitwistor description has both dotted and undotted spinors.
I see. And
then subject to an overall ambitwistor constraint, which is the one actually that I was showing you as the C constraint. Yes.
But this solves the second equation that you have. I mean, the one that is written. So the X
exactly.
Okay.
Yeah.
Thanks.
Alok Mishra, you have your hand raised.
Yeah, sorry. So I just had a question. So Rajesh, on the, if I remember correctly, in the math community, I think way back in the 80s, probably 88, somebody, I think by the name of Schmidt, so he was exploring a connection between essentially the algebraic geometry of moduli spaces, Riemann surfaces, using what was called as, I believe, I think Arkilov's intersection theory, involving determinate line bundles of Riemann surfaces, and this could actually be understood in terms of string partition functions. So I was wondering, is there some interest in the math community to study this duality that you suggest, purely from, let's say, intersection theory in the context of moduli spaces of Riemann surfaces?
Yeah, no, it's interesting you mentioned the Smith's paper. Smith was actually a physicist, theoretic. He was a string theorist by training. He now works in the Shell Corporation. So anyway, but Smith actually tried, as you said, to make sense of the so-called integer points in this moduli space. What he didn't realize at that time was that there's a geometric picture, the mathematically geometric picture to something called the Belly maps, which are precisely these points, which has been fleshed out in the maths literature. And there are people studying these very special points where the Strebel lengths are integers. They correspond to what are called arithmetic Riemann surfaces. And so these are a special set of points on the moduli space, and they begin to densely cover the moduli space as you take these lengths to infinity. It's related to a whole set of very beautiful mathematical results, which I don't have time to go into. But I think there is an interest there from the math side, from their own motivations. They have interest in studying many of these things, and I believe this will give the developments here will give a new angle to that. But of course, one has to communicate to mathematicians and get them in. But I believe it's a very fertile regime for this to happen.
Thank you.
Okay, very good. I think let's thank Rajesh once again for his very lucid talk and move on to the next session.
Thank you very much.